Hello everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be explaining the various named reactions with detailed mechanism for each of the reactions. So let us start with the first named reaction, that is aldol condensation. So aldol condensation is the addition of an alpha carbon atom of an aldehyde or a ketone to the carbonyl carbon of another molecule of the aldehyde or the ketone. And here the product is beta hydroxyaldehyde. So that's why we call this particular named reaction as aldol condensation. Ald for aldehyde and all for the alcoholic group. So beta hydroxy. So there is OH group and then there is aldehyde. So that's why the word aldol is given. Or beta hydroxy ketone also can be obtained. So but still we call overall we call this reaction as aldol condensation, although the beta hydroxy ketone also may be produced as the product in this particular reaction. Now, this is mainly catalyzed by either acids or bases. So here, first let us talk about the base catalyzed reaction, and then I'll be explaining about the acid catalyzed reaction. And once you get this beta hydroxyaldehyde or the beta hydroxy ketone, this aldol product on dehydration, that is by the loss of a water molecule, you can get alpha beta unsaturated carbonyl compound as the final product. That is, on heating this aldol, you can get the alpha beta unsaturated carbonyl compound by dehydration reaction. First, let us look into the base catalyzed reaction. So let me write the reaction first. So this is base catalyzed reaction. So let me take CH3CHO. Now, one more thing you have to clearly remember that the alpha carbon should have a hydrogen atom attached to it. At least one hydrogen atom should be there, which is attached to the alpha carbon. So this is the carbonyl carbon. So this is the alpha carbon. So there are 3 hydrogen atoms here. So without any doubt, the acetaldehyde undergoes aldol condensation. So we take acetaldehyde. I take 2 moles of acetaldehyde. Now, in the presence of the base, since I'm talking about the base catalyzed reaction here, you're going to get CH3, CHOH, CH2, CHO. So this is the alpha carbon, this is the beta carbon. So in the beta carbon, there is OH group, which is nothing but, now we have beta hydroxyaldehyde, which is nothing but the aldol. So let us name this particular compound. So there is in the third position. So if I start numbering 1, 2, 3. So in the third position, there is hydroxy group. So 3 hydroxy and totally there are 4 carbon atoms and it is an aldehyde. So butanol. Yes. So let us try to understand the mechanism of this base catalyzed aldol condensation reaction. So here, first I'm going to take the aldehyde. That is, let us learn the mechanism by using the acetaldehyde itself. So CH3CHO. Now, OH minus from the base, it abstracts one of the alpha hydrogen atoms. So now this bond shifts here. So now you can get here H, C double bond O. Now one of the hydrogen has been abstracted. So the minus charge is on the carbon atom and there are 2 hydrogen atoms that are there. So this is the carbanion. Now this can also be written as by the shifting of the charges. So this can shift here and this can shift here. So you can write it as C, here O minus, H, this can be double bond and CH and H, which is nothing but enolate ion. So next, coming on to the next step. So what is going to happen? Now let us take this carbanion. So H, C double bond O. Here there is H and H and there is a minus charge. Now this attacks one more acetaldehyde molecule that we are going to take. So as I already told in the general reaction which I have written that there were 2 moles of the acetaldehyde that were taken. So here we have CH3. So now this minus charge comes and attacks the carbonyl carbon and here this bond shifts towards the oxygen. So now we are going to get H, C double bond O. Here we have CH2, right? This is CH2. So I'm going to write CH2. Now this carbon has attacked the carbon and the carbon of another acetaldehyde. So this has become O minus. Here there is CH3 and there is also hydrogen which is attached. So now here what happens is next in the presence of water. So this O minus will be converted to H. So we are going to get CO. Here there CH2. Here OH and H and CH3, which is nothing but 3-hydroxy butanol, right? So this is how the base catalyzed reaction proceeds. Now, as I already told, the dehydration reaction can take place. So let us look into the dehydration reaction. So the same thing I'm going to take, that is 3-hydroxybutanol. So HCH2, right? Then we have OH and H and CH3. So there can be removal of water molecule. So what happens? This shifts here and this is removed off. So we get H, C double bond O. Here we have CH double bond CH and CH3. So here we have again the aldehyde group and we also have a double bond that is present here. So if I start numbering from the aldehyde carbon, 1, 2, 3, 4. In the second position, there is a double bond. So I'm going to name it as 2-butanol, right? So there is a double bond also and the functional group is aldehyde. So the name is 2-butanol. Next, coming on to the acid catalyzed mechanism. Acid catalyzed reaction, that is the aldol condensation. So here again the acid catalyzed aldol condensation, it generally generates aldols of the type alpha beta unsaturated carbonyl compounds. So let us start writing the mechanism. So first let us take CH3. So let us take a ketone now. So acetone in the presence of H plus. So it is very clear that the lone pair of electrons on oxygen will attack the H plus. So you're going to get here CH3. This remains the same. Here double bond O, H, and this becomes positively charged because the lone pair of electrons on oxygen is used for the attack. Now this can also exist as, so here this can shift here, the bond can shift here. So this can exist in this form also, that is CH3. Now this bond has been shifted, so this becomes single bond. Now this becomes OH. Now since carbon has lost the electrons, so it becomes positive. So in this case, we are talking about carbocation. So now let us write the carbocation. So CH3, C. There is one more CH3 that is present here and OH, right? And there is a plus charge. So we know that there is also the enol form that is present for that of the ketone. So here, let me write it separately so that it is more clear. So this is acetone. So the acetone can also exist in the enol form. How do we write it as? So this is the keto form. So this also can be written in the enol form as CH2 double bond C CH3 OH, right? Now if I take this here, and shift it here, it will become the keto form, right? I hope it is clear. So this is just for your information that I have written the enol form. How do you write the enol form for the keto? So let us take the enol form of acetone, of another acetone molecule. So CH3 and then we have OH. So this is the enol form. Now this bond shifts here. This bond attacks the carbocation. So now what is going to happen? Again, there is H plus that is present. So we have CH3, OH. Now the CH2 is attacking, right? So this double bond is attacking the carbon. So CH2 will directly bond to the carbon. So CH2. Now this becomes C double bond O and CH3. Right? So now we have got this ketone. This is the ketone. And in the alpha and then beta position, we have got the OH also. Now there is next step where the CH3, COH, CH3, CH2, C double bond O, CH3 in the presence of H plus, you're going to get, now this lone pair of electron attacks this H plus. So CH3, C, here it becomes OH2 plus, CH3, CH2, C double bond O, CH3, right? Now this OH2 can be removed as water molecule. So minus water molecule. I'll just erase this part since it is just, I've written this just for understanding about how to write the enol form. Yes. So by the loss of water molecule, now it becomes, so this here, the carbon is losing this water molecule. So this bond, whatever the water molecule is there, it is removed along with the electrons that are there. So the carbon will get positive charge. So CH3, here this carbon gets the positive charge. Now here CH3, again CH2, C double bond O, CH3, right? So now what is going to happen? So here there is the plus charge, there is CH3. Now there are two H atoms that are there. Let me show it in this step itself instead of writing it again. So the CH2, I'll just write it. I'll just show the two hydrogen atoms separately here, right? So this bond can shift here. So what is going to happen? I'll just show it here. So you're going to get CH3, C, CH3, here double bond, CH, CO, CH3, right? So you're going to get the alpha beta. So this is the alpha, this is the beta, right? So alpha beta unsaturated carbonyl compound. So here specifically we have taken the ketone. So alpha beta unsaturated ketone is obtained as the final product. So this is the final product that we get, right? And as I've already mentioned, in the acid catalyzed mechanism, we usually expect the alpha beta unsaturated carbonyl compound as the final product. Okay. Next, coming on to the retroaldol condensation. So here, the entire reaction of the aldol condensation is an equilibrium, including the dehydration. And hence, what happens is the alpha beta unsaturated and the beta hydroxycarbonyl compounds may be cleaved in the presence of the hydroxyl ion. So again, you may get back the carbonyl compound. So alpha beta unsaturated carbonyl compound, the beta hydroxycarbonyl compounds can be cleaved in the presence of the hydroxide ion because we are using the base catalyzed. So base is present, right? So again, the corresponding carbonyl compounds may be regenerated. So in other words, it is a reverse of the aldol condensation reaction. So this demonstrates that the aldol condensation is an equilibrium process. So even when I was writing the mechanism, I used the reversible arrow symbol for all the steps, right? So here the equilibrium process is observed in case of aldol condensation. So whenever the aldehydes or the ketones are obtained back from the products that were obtained from the aldol condensation, then that reaction, we call it as the retroaldol condensation. So let us write the reaction. So CH3, so CH3, here OH, CH2, CO, CH3, if I take. So here we know that beta hydroxy, here we have the ketone. So in the presence of OH minus, so you're going to get the ketone, that is acetone, you're going to get it back. So from 2 moles of acetone, you're going to get this, the beta hydroxy ketone. So again, on this retroaldol condensation in the presence of base, you're going to get back the acetone. So whenever you are taking a mixture of two aldehydes, which in case both of them possess alpha hydrogen atom, then you're going to treat it with a base. You're going to get 4 different aldol products, right? So let us talk about the crossed aldol condensation. So this occurs between the 2 different aldehydes or ketones. Now, if both the reactants contain alpha hydrogen atoms, then up to 4 different aldol products may be formed. Now, how do you improve the selectivity? So instead of getting 4 different variety of products. If you want to improve the selectivity, if you want certain products only, then what you can do, you can select one aldehyde without alpha hydrogen atoms. So this aldehyde, which does not have the alpha hydrogen atoms, so it will be only used for the attack of its carbonyl carbon. The base does not abstract any hydrogen from it because there is no alpha hydrogen at all. So this aldehyde will be only, the carbonyl carbon of this aldehyde will be used for the attack by the carbanion if I'm taking the, if I'm considering the base catalyzed mechanism. So here you can also use excess of non-enolizable aldehyde, that is the aldehyde without the alpha hydrogen atom. So under these conditions, a single major crossed aldol product is obtained. So now let us look into the example. So if I take CH3, CHO and treat it with formaldehyde, then you're going to get one major product. So what is the main product? So let us write the mechanism and let us try to find out. So it is very clear here there is no alpha hydrogen. Here there is alpha hydrogen is present. Here it is present. And here it is absent. The alpha hydrogen is absent. So this formaldehyde is only used in such a way that the carbonyl carbon of this formaldehyde is used for the attack by the carbanion. So let us consider the base catalyzed mechanism. So here, let me write the alpha hydrogens clearly. So now in the presence of base, so this base, it abstracts one of the hydrogen. So now we are going to get CH2 minus CHO, right? So now this can attack the formaldehyde. Now there is no alpha hydrogen here. It is very clear that in this case there is no alpha carbon at all. So there is no question of the presence of alpha hydrogen. So now this can attack the carbonyl carbon. So now you can get here CO minus, here H and H, here CH2 and CHO. Right? So now in the presence of water, what you're going to get? C, here this becomes OH, H and H. So here C, H and H is present. And then we have the CHO. Now it can also lead to the loss of water molecule. So water molecule can be lost on heating, right? So this can shift here. This OH can be removed off. So we have CH2 double bond CH, CHO, right? So we have the single major product, that is acrolein, that is obtained here since I have taken a non-enolizable aldehyde here. Okay, so the product here is CH2 double bond CH, CHO. So if I would have taken another aldehyde which has the alpha hydrogen atom, then you would have got four different products because the abstraction of the proton can take place from any of them. So the attack to the carbonyl carbon also can occur, and because of which there are four different aldol products that are possible. Here, since I have considered one of the aldehyde which does not have an alpha hydrogen atom, so you can easily see that there is one major product that is obtained in this particular reaction. Next, coming on to Claisen-Smith reaction. So here, this is again an example for a crossed aldol condensation reaction. Here you're going to take the aromatic aldehyde or the ketone, and you're going to select an aliphatic aldehyde or ketone which contains alpha hydrogen. So this has to be kept in mind, right? And again, we are going to carry this particular reaction in dilute alkaline medium. Typically, the 10% NaOH is taken and low temperature conditions are maintained. So here, a cross-aldol product is formed, that is beta-hydroxycarbonyl compound. Then what happens? Again, the dehydration occurs to form the alpha-beta unsaturated aldehyde or the ketone. So this is again useful for the synthesis of alpha-beta unsaturated carbonyl compounds, that is alpha-beta unsaturated aldehydes or ketones. So let us look into the general reaction. So taking here the aromatic aldehyde, and then we have to take the aldehyde or ketone having the alpha hydrogen. So let us take acetaldehyde. So 10% sodium hydroxide and room temperature. As I already told, low temperature is required. So here, usually the reaction is very slow. It takes, in this condition, it takes around 8 to 10 days to complete. So we have C6H5, CH, double bond, CH, CHO, which is nothing but cinnamaldehyde. Yes. Coming on to one more example where C6H5CHO, you're going to take benzaldehyde. Now, instead of acetaldehyde, if I take acetone, CH3COCH3, again 10% NaOH, and here maintaining the temperature as 30 degrees Celsius, and this completes at around 2 to 3 days. So here you're going to get the product C6H5, CH double bond, CH. Same like this, but instead of H, we will have a CH3. So CO, CH3. So this is nothing but benzol acetone, right? So let us look into the mechanism. It is very simple. We have already studied in detail about the aldol condensation. So it is similar to that what we have studied. So first let us take the acetaldehyde, CHO. Now in the presence of base, now what happens? The base abstracts one of the alpha hydrogen and this shifts here. So you're going to get CH2, CHO. Now there is a carbanion that is formed. Now this can react with the benzaldehyde, that is C6H5CHO. Now here this can attack the carbonyl carbon. This shifts here. So we have C6H5. Now this becomes O minus. Here there is H. Now here there is CH2, CHO. Now this in the presence of water. Like how we have written for aldehyde, aldol condensation, the same thing we are following here also. So here we have COH, H, and then we have H and H, CHO. Now, the removal of the water molecule can take place. So, here we have, now what happens? This moves here and this OH is removed off. So, we have CH double bond CH, CHO, right? That is cinnamaldehyde is obtained as the product. Yes. Now coming on to the applications of this particular reaction. So suppose you take C6H5CO CH3. Along with that, you take C6H5CHO, that is the benzaldehyde. Now in the presence of NaOH and in the ethanol solvent, you're going to get C6H5CO, CH double bond CH, C6H5. So this is nothing but benzal acetophenol, which is also called as chalcone, right? Now, this is one of the applications. So you can prepare chalcones, wide variety of compounds with different substituents on the benzene ring. So you get chalcones by this particular mechanism. So now, if you're taking citral, so here we have CHO, double bond, CH3, here double bond, and here there is, yeah, 2 methyl groups. So this is citral. Next, if you're treating this with acetone, CH3, COCH3. Now, in the presence of sodium ethoxide and ethanol, so you're going to get beta ionol. So here, this we have these 2 methyl groups, double bond O, CH3, and here we have CH3 and also the alpha beta unsaturated compound. So because of which we get this beta ion, which is an important intermediate in the synthesis of vitamin A, right? So coming on to Staube condensation reaction. So this condensation is between the dialkyl succinate or the derivatives of this dialkyl succinate and the aldehydes or ketones in the presence of a strong base. So the base that can be used are sodium hydride, sodium ethoxide, etc. And they give the salts of alpha beta unsaturated half esters. So alpha beta unsaturated half esters are produced by this reaction. And this is also an important carbon-carbon bond forming reaction which is used in organic synthesis. So let us look into the general reaction. So here you're going to take dialkyl succinate. So let us take diethyl succinate, or in general I can take as dialkyl succinate. The reaction of this or its derivatives with aldehydes or ketones. And again, strong base is required. So keeping these things in mind, let us try to write the equation. So here, so let me take a ketone. Now I take diethyl succinate. So CH2, COO, C2H5, CH2, COO, C2H5. This is nothing but diethyl succinate in the presence of a strong base. So you can take any of this sodium hydride or sodium ethoxide. So let us take sodium ethoxide, C2H5ONA. So you're going to get R, here Cr, this becomes OH. Now here CH, CH2, COONA. Now this CH, COO, C2H5, removal of water molecule. You're going to get R, C, R. Here there is OH and one H, so easily you can predict where there will be removal of water molecule. So double bond C, CH2, COONA, and here COO, C2H5. So you're going to get the half esters as the product. So let us try to write the mechanism of this reaction. So first let us take the diethyl succinate. So CH2, COO, C2H5. Again CH2, COO, C2H5. Now in the presence of the base, that is C2H5ONA, what is going to happen? One of these hydrogens, any one of these hydrogens can be abstracted. So let us consider one of the hydrogen from this carbon has been abstracted. So you get CH2, COO, C2H5, and here CH. Now this becomes carbanion, COO, C2H5. So this is nothing but the carbanion, right? So one of the hydrogens can be abstracted by the base, that is the ethoxide ion, and you get the carbanion. Now this carbanion can attack the ketone. So let us take the ketone. Okay, so we have R, C double bond O, R. So this can attack the carbonyl carbon and this bond can shift here. So let us write, I'll write it here below. So carbon, the two R groups that are attached to the carbon. And then we have the O, which has the minus charge. Now to this carbon, this entire group has been attached. So let me write it here. So CH, here we have, to the CH, there is one group that is attached, that is COO, C2H5. Now the other group that is attached is CH2, C double bond O, O, C2H5, right? Yeah. Now, why I have written this is I can easily show how the minus charge now attacks the another carbonyl carbon and how the arrangement, how the reaction will proceed. So now this minus charge, it can attack this carbonyl carbon. So once this attacks, this can be removed off easily. So we have here C, R, and R. There is O that is present here. Now this O is connected to the C double bond O group. Now we have carbon. There is CH2 group and this bond. Now to this carbon, there is also H that is attached and COO, C2H5, right? So we know that this is nothing but the lactone. Now here, the OC2H5, this ion was removed off. Now this ion is still there, right? In the reaction mixture. Now this attacks this ion. It abstracts this hydrogen. So this bond comes and shifts here and this bond breaks. So we have R, R. So now this becomes a double bond, right? So now we have carbon, COO, C2H5. Now to this carbon, there is also a CH2 group that is attached. Now CH2 COO minus. So the COO minus can be neutralized by the Na plus that is present here. So I can also write it as CH2 COO N. So this is the final product that we get by this particular Staube condensation reaction. Right, Claisen condensation reaction. So here, Claisen condensation is nothing but the base catalyzed condensation of the esters, and compulsorily these esters should contain alpha hydrogen atom. So here, mainly this type of Claisen condensation can occur between the two molecules of the same ester, where we call it as self-condensation. So it can also occur between two different esters, where we call it as crossed Claisen condensation. And here the product that is formed is beta keto ester, which is a major product. And this is also an important carbon-carbon bond forming reaction that is used in organic synthesis. So let us try to understand the reaction as well as the mechanism in detail. So as I already told, here we are going to take esters. So let us take the ester ethyl acetate. So CH3COO, C2H5, that is ethyl acetate. I'm going to take another molecule of the same ester, that is CH3COO, C2H5, that is ethyl acetate, in the presence of base, because base catalyzed, right? So I'm going to take ethoxide ion. So sodium ethoxide can be taken. So in the presence of the base, you're going to get the beta keto ester as the product. So you're going to get the product CH3CO, CH2, COO, C2H5. And along with that, we're also going to get ethanol. So this is nothing but, see, you can see here, this is ethyl, this is aceto, again acetate. So ethyl, aceto, acetate. So this is the product. And why do you call it as a beta keto ester? See here, this is the ester the carbon, the functional group, right? So this is the alpha, this is the beta carbon with respect to the ester functional group. So in the beta carbon, you can see it is the keto group. So beta keto ester is the product that is obtained, right? So let us look at the mechanism of this reaction. So first, we are going to take the base C2H5O minus, which attacks the ester. So let us take the ester. So CH3, COO, C2H5. So ethyl acetate I have taken, right? Now this minus this base, it abstracts the hydrogen and this shifts here. So you're going to get CH2 minus charge. So again, you're going to get the carbon ion. So here C double bond O, O, C2H5. So along with that, now since the minus charge has abstracted the proton, so you're going to get C2H5OH. Correct? So now this carbon ion will attack now another ester. So let us take the carbon ion. So let me write it the other way around. So CH2 minus C double bond O, O, C2H5. Now I'm going to take another molecule of the ester, that is CH3, COO, C2H5. So now this minus charge, the carbon ion, it attacks the carbon in carbon. This can shift here. Same like how we have written for the aldol condensation, somewhat similar mechanism. So we have here CH3. This becomes O minus. Here there is O, C2H5. Now here there is again CH2, C double bond O, O, C2H5, right? So now it is very clear, this is a leaving group, right? Leaving group. So this comes back and this is removed off. So what you're going to get here, there is removal of the C2H5O minus ion. since it is a very good leaving group. So we get CH3, C. Here there will be double bond O, CH2, CO, O, C2, H5, right? So now, again, we know that the base is there, that is the ethoxide ion, which can again abstract the hydrogen. So here there is the hydrogen which can easily be abstracted. So in the presence of this base, that is C2H5, O minus, one of the hydrogens can be abstracted. So you can get CH3, C double bond O, CH minus, CO, O, C2H5. Now, this on acidification, we're going to get CH3, CO, CH2, COO, C2H5, which is nothing but the beta keto ester. Beta keto ester, or to be specific, this is nothing but ethyl acetoacetate that is obtained as a product by the Claisen condensation reaction of 2 moles of ethyl acetate. Next, coming on to Norvenagel reaction. So here, the condensation of the reactive methylene compound like malonic ester takes place with the aldehydes or the ketones. So here, again, this is a base catalyzed reaction. So it occurs in the presence of a weak base. And the base catalysts that can be used are aniline, alkylamines, pyridine, piperidine, etc. Now here, in this case, we know that the ketones are less reactive, which is again due to the steric hindrance. So we are going to take the highly active methylene compounds for this particular reaction. So again, it is particularly useful with the aromatic aldehydes. So you get good yield of products by making use of this particular reaction. So now, let us look into the general reaction. So C6H5, CHO. So we are going to take the benzaldehyde. Now, as I already told, we are going to take the reactive methylene compound. So we are going to take the malonic ester, which is a reactive methylene compound. So let us take the malonic ester itself. So CH2, COOR, COOR. This is the malonic ester. In the presence of a weak base, like let us say pyridine, or you can also use piperidine, any one of them. So you're going to get C6H5, CH double bond, C, COOR twice. Now this on acidification, that is H2O, H plus, and the second step, that is heat and the removal of carbon dioxide, you're going to get C6H5, CH double bond, CH, COOH, which is nothing but cinnamic acid. Cinnamic acid. So let us look into the mechanism of this reaction. So you can take tertiary amines as the base. So let us take tertiary amine here. Let me take the malonic ester. So we have CH2, COOR and COOR, right? So this is an active methylene group. So obviously we know that one of the hydrogens will be abstracted by the base. So you're going to get R3NH. This becomes positively charged. Now one of the hydrogens has been lost. So you're going to get CH here, the minus charge, COOR and COOR. Now this carbanion can attack the aldehyde or the ketone which you're going to take. So let us take the aldehyde. Let me write the general formula, R dash C double bond OH. So we are taking this carbanion now. So COOR and COOR. Now this attacks the carbonyl carbon and this bond shifts here. So you're going to get here R dash CO minus H, here CH, COOR, COOR. Now, what is going to happen is, now there is a minus charge on the oxygen. So we know that there is also this particular, the tertiary amine which has been protonated. So we have this R3NH, right? So this H plus from this R3NH can combine with this O minus, right? So you can get R dash C OH H CH COOR COOR. Now, this can lead to the removal of water molecule. Now, there is one hydrogen here and there is OH group here. So, a water molecule can be removed off. So, it can give you R dash CH double bond C. Here there is COOR and COOR, right? So, now this on first step, that is acid hydrolysis, and second step, that is heat and removal of carbon dioxide. So we know that we are going to get R dash CH double bond CH COOH, right? There is a removal of the carbon dioxide molecule, and of course the first step is the acid hydrolysis, because of which we are going to get the alpha beta unsaturated carboxylic acid. So now again you have to remember that due to the steric hindrance, the ketone is less reactive. I've already told you about this. So in such cases, the more reactive methylene group is used. Okay, so let us try to write the reaction for this. So let me write it here. So in case of, let us say, acetone, so a ketone whenever it is used, so there is more steric hindrance when compared to that of the aldehydes. So we are going to use the methylene active methylene group, which is again more reactive. So COOR, so here the CN group is present. So a more reactive active methylene group is taken whenever you're going to select the ketone. So again, in the presence of CH3CONH2, the base. So here you're going to get C, here CH3, double bond. So here C and CN and COOR. Now the next step is, first step, you're going to take water and H plus, that is acid hydrolysis. Then the second step is heat and decarboxylation occurs. So you're going to get here CH3, double bond, now CH, COOH, right? So this is nothing but, so let me write it clearly. So this is nothing but, here we have, see, 1, 2, 3. So in the third position, there is methyl group. So this overall is crotonic acid. So 3-methyl crotonic acid. So crotonic acid is obtained. So again, I repeat, the Love-Nagel reaction, it is more useful when you take the aromatic aldehydes as the substrate. Okay, so this is with respect to the Love-Nagel reaction. So let us look into the next reaction, that is Darson condensation. So here, the condensation of the aldehydes or the ketones with the alpha halo ester takes place. And here again, the condensation takes place in the presence of a base. And here we get alpha beta epoxy esters as the product. Or we are also calling them as the glycidic esters. So this reaction is nothing but the Darson condensation reaction. And here we are going to get the epoxide containing compounds. So this is one of the important methods of preparing epoxide containing compounds. So let us write the general reaction. So let me take a ketone. Now, aldehyde or ketone is treated with alpha halo esters. So let us take the ester. So here, instead of CH3, so this is CH3, COO, C2H5. This is the ethyl acetate. So now alpha halo. So I'm going to replace one of the hydrogen with any halogen atom. So I've written this just for you to understand. So let me replace one of the hydrogen with the halogen. Let me take chlorine. So this is nothing but ethyl. Here this is chloroacetate. Okay. So this in the presence of base. So we are going to get the alpha beta epoxy ester. So CH here epoxide. So again R and R. So here COO C2H5. So this is the ester group. Now alpha beta. So in the alpha beta position, you can see the epoxy group that is formed. So here the product that is formed is alpha beta epoxy ester. So now coming on to the mechanism of this reaction. So as I already told, we are going to take the alpha haloester COO C2H5, and here there is a chloro group that is attached. Now in the presence of the base, so let us take the base. So here the ethoxide ion is taken. Now this base abstracts one of the hydrogen. So we are going to get CH minus here Cl, now COO C2H5. Now we have to take the ketone or the aldehyde. So let us take the ketone RCOR. Now this comes and attacks the carbonyl carbon. This shifts here. So we are going to get here RCR. So this becomes O minus, right? Now to this carbon, the CH is attached. So CH, which has fluoro group that is attached, and COO C2H5. Now this O minus attacks this carbon since it has a chloro group that is attached, and chlorine can be easily removed off. So Cl minus is removed. So you're going to get R, C, here R. Now this single bond remains, and here the oxygen is forming the bond with carbon, right? And H is there. Along with that, COO C2H5. So this is nothing but epoxy acetic ester. Correct? So I hope it is clear how to write the mechanism for the Darcy condensation reaction. Next, coming on to Dickman condensation. So this is an intramolecular Claisen condensation of diesters, that is dibasic esters. Now here, this is also like Claisen condensation itself. So that's why we call it as a type of intramolecular Claisen condensation of the diesters. And the product here is the cyclic beta ketone derivative. Okay, so we have to remember here beta keto ester, and especially the cyclic derivative is obtained. And here we can use the common bases, that is sodium ethoxide, sodium hydride, potassium tertiary butoxide, etc. So let us write the general reaction. So let me take CH2. So it can be N times, so it can be anything. So CH2, COO, C2H5. So based on the number of carbons that are required in the ring, so based on that, you can take this N. So again, CH2, COO, C2H5. In the presence of a base like C2H5, ONA, so you're going to get CH2 N times here CH2. So here CH, COO, C2H5, and here these two carbons are held together by the C double bond O. Now, how I have written this is, so this is the ester group. So we have beta keto ester. So this is the alpha carbon. This is the beta carbon. So this is the keto group. So beta keto ester. And one more thing is that you should get a cyclic ester, right? So based on that, just N can be the number of, you can take the number based on how many atoms should be there in the cyclic structure that you're going to prepare. So based on that, N is substituted. So based on that, you're going to get this particular product. So let us take a specific example. So suppose you take CH2, CH2, COO, C2H5, again CH2, CH2, COO, C2H5. In the presence of this C2H5 ONA, that is sodium ethoxide. So here, you just count if one of them is converted into the keto group, and one OC2H5 minus will be removed off as a leading group. So then this ester group remains as such. So this should be the beta keto ester. So this of course will be the alpha carbon. So now how many carbons will be there in the ring? So this will be the part of the ring, 2, 3, 4. So 4 as well as this 5. Right? The alpha carbon also, here in this case, you have seen that the alpha carbon also is a part of the ring. So 5. 1, 2, 3, 4, 5. So 5-membered ring. So, correct. So this is the alpha carbon if I'm considering. So here, this is the alpha carbon. So to this, I have COO, C2H5 that is attached. Now, in the beta position, there is a keto group. So now I have got the beta keto ester That is the cyclic beta keto ester that is obtained. So now coming on to the mechanism. So let us take, so CH2, CH2, COO, C2H5, CH2, CH2, COO, C2H5. Now in the presence of the base, what is going to happen? So let me take the base C2H5, O minus. So here, this hydrogen is abstracted. Okay. So now what has happened? This H2, CH2 will become CH. Now there will be minus charge on the carbon. So let me write it. So here CH2, COO, C2H5. Now here CH2. Again we have CH2. Now this CH2 becomes CH minus, right? Then we have again COO, C2H5. Now this minus charge, it attacks this and this becomes the minus O minus. Now count the number of carbon atoms that are forming the ring. 1, 2, 3, 4, 5, right? So I'll directly write the 5-membered ring, right? 5-membered ring structure. Now here I have O minus, here I have OC2H5. Now to this carbon, there is COO, C2H5 that is attached. Now this minus can come back here. This can be removed as a leaving group, that is OC2H5 minus is removed off. So you're going to get here, okay, 5-membered ring. Now this becomes double bond O. Now this is COO, C2H5, right? So this is nothing but the beta keto ester. Right? Now, there is also possibility of continuation of this particular reaction. So we know that there is hydrogen that is present here. So this hydrogen, here the hydrogen can be removed as proton and this bond can be shifted inside. So minus H plus. So we can get here double bond. Now, if this is moving here, this has to move. The bond has to move to the oxygen. Again, it becomes a charge O minus. Now this will be again COO, C2H5 as how it was there in the previous step. Now this on treating with acid in the presence of water, right? So H3O plus hydronium ion. So this was minus charge here. Now again, you're going to get double bond here and this H as well as this becomes COOH, right? This will be the COO C2H5 will be converted to COOH group. Now this can also, what happens is the decarboxylation reaction can take place, that is removal of the carbon dioxide. So this can be removed of CO2. So you can get the cyclopentanone. Let us look into one more example of this particular reaction. So let us take C2H5, COO, CH2, CH2, here C double bond O, OC2H5, right? Which is nothing but ethyl succinate. Now this on treating with C double bond O, again OC2H5, CH2, one more molecule, so CH2, COO, C2H5. Now, this in the presence of C2H5 O minus. So this base can abstract one of the hydrogens from here. So it can become CH minus, right? So let me write it. C2H5, COO, here CH2. Now here CH2. Again, I'm continuing it here. So C double bond O. Now, this minus, whatever is there, it attacks. So now let me write it here itself. Okay, so that I can reduce the number of steps. Now this becomes minus. This attacks the carbon in carbon and this leaving group is removed off, right? So now this CH attacks here, the CH, COO, C2H5. Now to this CH, the CH2 is also attached. Then we have the COO, C2H5, right? So now what happens again in the presence of the base C2H5, ONA. right? Yes. So C2H5ONA, what you're going to get? See here, you're going to get the cyclized product. So C2H5COO, here, this becomes, now here the cyclization takes place. Now here, this becomes minus charge because of the abstraction of the proton by the base. So here, let me show the steps here itself. So here, this minus, it attacks. After attacking, this OC2H5 minus is removed off, right? So let me write the product, keeping this in mind. So we have again CH here. Then here there is C double bond O, which is connecting to the other carbon, right? So we have, this is the CH2 group, which is connected to that carbon. So CH2. Then to the CH2, we have CH, COO, C2H5. Now to this carbon, there is CH2 that is attached. And here we have C double bond O, right? So how do we name this particular compound? So this is cyclohexane structure. Then we have, suppose we are going to number it. So let us start from this, numbering from this carbon based on the substituent that is present. So 1, 2, 3, 4, 5. So in the 2 and 5 position, there are ketone substituents, ketone groups. And in the first and the fourth position, we have the carboxylic ester groups, right? So we can write it as cyclohexane 2,5 dione 1,4 dicarboxylic ester, right? So this is how we are going to prepare this particular compound by making use of this particular reaction. Next, coming on to the Perkin condensation reaction. So this is the reaction of the aromatic aldehyde with an aliphatic acid anhydride. So these are the two reactants that we need to consider. And here, the presence of the sodium or potassium salt of the acid is required. So mainly, here the reaction between the aromatic aldehyde and the aliphatic acid anhydride takes place, and the sodium or potassium salt of the corresponding acid have to be taken so as to produce the alpha beta unsaturated carboxylic acid as the product. So this is also an important method for the synthesis of cinnamic acid and its derivatives. So let us look at the general reaction. So C6H5, CHO. So let us take the acetic anhydride. So CH3, CO twice O. This is acetic anhydride. Now, the sodium or potassium salt of the corresponding acid. So the acid that has, this is acetic anhydride. So I'm going to take the sodium or potassium salt of acetic acid. So let us take CH3COANA, sodium salt of acetic acid, that is sodium acetate, and heat it. So we are going to get C6H5, CH double bond CH, COOH, that is cinnamic acid. Along with that, we are also going to get acetic acid. If I take furfuran, so furfuran is with CHO. Now, in the presence of acetic anhydride, CH3CO twice O. So again, in the presence of acetic, that is sodium acetate, that is the sodium salt of acetic acid, and heat, we are going to get here the furan ring. Along with that, CH double bond CH, COOH. This is nothing but furfuran acrylic acid. Furfuran acrylic acid. Let us look into the mechanism of this reaction. So first, let us take the acetate ion, that is from the sodium acetate that we have taken. So let me just show how it is formed. So CH3 COONA, we know that it will give CH3 COO minus plus Na plus. This we already know. Now this acetate ion, on treating with the acetic anhydride, so we know that, let me just show one more hydrogen separately. Then CO, O, CO, CH3, right? This is acetic anhydride. Acetic anhydride, or this acetate ion, it will abstract the hydrogen here. So this will shift here. This particular acetate ion, okay? So it abstracts the hydrogen. So you're going to get the carbanion that is present here. So now what you're going to get? CH3, COOH, right? Acetic acid, because the hydrogen has been abstracted, the proton is abstracted. And now you're going to get the carbanion, that is CH2, here minus COO, COCH3, right? So now this carbanion will attack the carbon in carbon of the aldehyde that we are going to take, right? So here C6H5, let us take benzaldehyde. So here this carbanion is going to attack the carbon in carbon. Okay, so CH2, COO, COCH3. So this attacks the carbon in carbon. This bond shifts here. So here you're going to get C6H5, CO minus. Here that will be H. Here CH2, CO, O, CO, CH3. Now in the presence of acetic acid, there is acetic acid that was produced here. Now this O minus will be converted to OH. So I'm going to get C6H5. Here OH, H. Here I can write it as CH and H, right? Then CO, O, CO, CH3, right? Now this H can shift here. This OH can be removed off. So you can remove the water molecule on heating, right? So you're going to get C6H5, CH double bond CH, here CO, O, CO, CH3. Now this on hydrolysis, you're going to get the acid CH, CH, here COOH, this hydrolysis. Now CH3CO also you're going to get the CH3COOH. Okay, so this is how you're going to get the final products from the starting materials, that is the anhydride, that is the anhydride, along with that the sodium or potassium salt corresponding to that particular carboxylic acid, and the aromatic aldehyde. Next, coming on to Riemann-Tiemann reaction. So here the reaction of phenol with chloroform in the presence of aqueous alkali, that is sodium hydroxide or potassium hydroxide, to produce orthohydroxy benzaldehyde, that is salicylaldehyde, and a small amount of para-hydroxy benzaldehyde. So this is called as a Riemann-Tiemann reaction, and it is an important method for the formylation of the phenols. So here mainly the CHO group is added to the phenol in the ortho position, and some amount of the para product is also obtained as the product. So let us write the general reaction for this particular Riemann-Tiemann reaction. So we take phenol in the presence of chloroform, and you can take NaOH or KOH. Let us take sodium hydroxide, 60 degrees Celsius. So you're going to get ortho-substituted phenol, that is the ortho-hydroxy benzaldehyde. So this will be the benzaldehyde. Now, the ortho-hydroxy is taken, or you can also call it as salicylaldehyde. This is a major product. And the para-substituted product, that is OH, and here CHO, which is the minor product, right? So let us look into the mechanism of this reaction. So CHCl3 in the presence of OH minus, that is from the base. So here you're going to get, so here this will be C minus, and here Cl2, Cl. Now the H will be abstracted so that water will be removed off. So this becomes the minus charge. Now this Cl also can be removed off, that is minus Cl minus, because of which you get the dichlorocarbene. So this you're going to get dichlorocarbene. Now we are going to take the phenol OH in the presence of OH minus. Now what is going to happen? The H will be abstracted. You get the phenoxide ion. So let me write the phenoxide ion. So O minus, right? So this minus can shift here. So this can shift here. So this, there can be resonance that is possible here. So here minus, here double bond O. Here this also can shift inside. This can shift here. Now you can also write it as this here minus, here double bond, here also double bond O. Now this can shift here and this can shift here. So these are the resonance structures. So now in the presence of this dichlorocarbene, what is going to happen? Now here double bond O, here there will be H. Now we are showing, I'm just showing the auto substitution. So H here, now this dichlorocarbene, so here you get the CCl2, right? Now here there is minus. So in the presence of water, now what is going to happen here is this moves here, this moves here. So you're going to get, so here the H will be attached to the CCl2. Okay, so here you get O minus. Here the bond comes in. Now this will be CHCl2. So this on hydrolysis in the basic conditions, of course. So you're going to get here OH and CHO. So that is what the final product, that is salicylaldehyde. Aldehyde. Okay. So this is how we obtain the final product, that is salicylaldehyde, by taking phenol as the starting material and by making use of chloroform as well as in the presence of a base. Next, coming on to Reformatsky reaction. So the reaction of the alpha haloester, usually we take the alpha bromo ester with carbonyl compounds, that is with an aldehyde or a ketone in the presence of zinc metal and inert solvent. So we get the one intermediate is obtained, and the hydrolysis of that intermediate will give you the beta hydroxy ester. So this is again another useful carbon-carbon bond forming reaction that is used in organic synthesis. So let us look into the general reaction and write the reaction here itself. So we need to take the carbonyl compound and it is made to react with the alpha haloester, right? So let us take the ester. So let me take CH3, COO, C2H5, that is ethyl acetate. Now alpha halo. So this is the alpha carbon with respect to the ester functional group. So alpha halo. So for this carbon, I need to connect the halogen. So let me do the required adjustments. So CH2, here it will be bromine. Right. Usually we take the alpha bromo ester. So that's why I've taken the alpha bromo ester. Now in the presence of the zinc metal, so zinc, and we are using an inert solvent like benzene. Second step, as we already know, the hydrolysis has to take place so that we get the final product, that is beta hydroxy ester. So beta hydroxy. So now ester is here. In the beta position, there is hydroxy group. So CH2, COO, C2H5. So this is the alpha carbon. This is a beta carbon. So there should be hydrogen, the hydroxyl group. So the R groups will be attached here. So this is nothing but beta hydroxy ester. Yes, coming on to the mechanism now. So let us take here CH R dash. So let us take one bromo atom that is present in the alpha position of the ester. So let C2H5. In the presence of zinc and benzene. Now what happens here is, so bromine, the zinc inserts here in between the carbon and the bromine, and the other things remains the same. CH, COO, C2H5. Now the carbonyl compound is taken, which reacts with this intermediate, CHR dash, COO, C2H5. Now what is going to happen is that C, R and R. So this bond shifts here. So because of that, here O, Z and Br, and here the other part connects it to the carbon. So CH, R dash, COO, C2H5. This on hydrolysis. So this is the intermediate that we get. this intermediate, this on hydrolysis, you're going to get the required product. That is R. Here we have again one more R. Here OH, CH, here R dash, COO, C2H5, which is nothing but the beta hydroxy ester. In case of sterically hindered carbonyl compounds like ketones, so let me add something here. So this, suppose we take ketones, that is sterically hindered ketones. So the reaction is not possible. So the same ester reacts to give the beta keto ester. So let us look at the mechanism for that. So let me erase it here and let me write the reaction for that. So suppose you're going to take, so here Br, and let me directly write whatever is obtained in the first step. So Zn, here the insertion has already taken place. R dash COO ethyl group. So now what is going to happen? This BrZn, so CH R dash. So here the other ester also, it reacts with each other whenever you're going to take the sterically hindered ketones. So COOET. Now on hydrolysis, that is HCl and water, we're going to get R dash CH2 C double bond O CH R dash COOET. That is, you're going to get, see here, this is the alpha, this is the beta. So beta keto ester. Here you're going to get beta keto ester. Along with that, you're also going to get ethanol and 2 moles of ZnBrCl, right? So let me balance the equation. So here also you're going to take 2 moles of this particular, the product that is obtained in the first step, right? So next, coming on to the Diels-Alder reaction. So this is the 1,4 addition of the unsaturated molecule, that is dienophile, with a conjugated diene, so which we call it generally as a diene. So diene and dienophile, the cycloaddition reaction between these two, that is especially the 1,4 cycloaddition or 4 plus 2 cycloaddition, whatever you call it as. So you get ultimately a 6-membered cyclic product as the final product because of this cycloaddition reaction. So this is called as the Diels-Alder reaction. They are also, this type of addition is also a pericyclic reaction. And again here, the syn addition takes place. Here also, carbon-carbon bond formation is taking place, and because of which we're going to get the cyclohexene and the derivatives of the cyclohexane. So let us take the example. So here, CH2, CH, here CH2. Okay, let us take one more, that is CH2, CH2. So cycloaddition between a conjugated diene. So here we have a diene and it is conjugated. The double and single bonds are conjugated with respect to each other. And a dienophile. So here I'm going to take the dienophile, okay, the unsaturated molecule. So now how the reaction can proceed. So here this takes place, this here and this way. So because of which you're going to get the cyclohexene. So here there is a double bond that is formed, and in all other cases, it is converted into a single bond. So you get a cyclohexene. But here the yield is less, that is 20%, and at 200 degrees Celsius. Let us take one more example. Let me write it here. So suppose you want substitutions. So we take here CH, CH, here CH2. Let us take here CH, double bond CH2. Here there will be a substituent that is added CHO. Now again, this is for carbon, okay, how it is attacking. This shifts here. Let me write it clearly. So CH2, this attacks the carbon, this attacks here, and this can attack this carbon. So because of which you're going to get here the cyclohexene with the CHO group, right? So this is again carried out at 160 degrees Celsius. Now, in the case of the dienophiles, if I'm considering, the simplest unsubstituted alkene, that is, you can take ethene, but usually ethene, it acts as a poor dienophile, but still you can use ethene as a dienophile. And most of the reactive dienophiles are the ones which have one or two electronegative groups, which are alpha to the unsaturation. So for example, you can have, now suppose if this is the unsaturation that is there, so if Z is an electronegative group that is added, so because of which the reactivity goes on increasing. Or you can also add two different Z groups, okay, Z and Z dash, which increases the reactivity of the dienophiles. Now the Z and Z dash can be any one of this. You can use CHO, you can use COR group, you can use COOH group, you can use COOR, COCl, CN group, NO2 group, X, that is halogen, or you can add one more C double bond C group that is added to this particular the dienophile, so that to make it more and more reactive. Okay, so you can add any of these different groups. So most reactive dienophile is the tetracyanoethane. Ethene. Okay, tetracyanoethylene or tetracyanoethene. So where four cyano groups are attached to the ethene, so because of which it acts as a very reactive dienophile. And most commonly used dienophiles are malic anhydride as well as the quinones. When I'm talking about the dienes, okay, so let us look into what are the different compounds that we can use as dienes. So it can be a conjugated diene, or you can use a polyene, or enine, or dienes. So any of these, okay, dienes. So now, which are the different possibilities? So here you can use such type of compounds. You can also use cyclic compounds. Here also there are two double bonds. It's a diene. So you can also use here in this way, where here you have a double bond and here again in conjugation with each other, right? And here, in this case, the two cyclic rings join together. Again, here also there is conjugation with each other. And then even furan, where there are two double bonds, right? And here, when you're talking about a dienophile, which contains a C double bond C bond, can also act as a diene if used under suitable conditions, right? So, suppose we have C. This is the diene. You can also use here the double bond on either side, C double bond C on either side. So where this is used as a dienophile. And this is a diene. So here also you can see there are two double bonds which are in conjugation with each other, but still it is acting as a dienophile, right? So in this case, you're going to get the product in this way. Okay, so this is the adduct that is formed. So if I'm talking about aromatic compounds, the aromatic compound can act as a diene only when it has at least three benzene rings which are fused linearly. For example, if the three benzene rings are fused like this in a linear fashion, then it can act as a diene. So suppose it is in this way. Okay. So in such cases, the aromatic compounds can also act as dienes. Now, talking about the mechanism of this reaction. So the first type of mechanism was given by Broadley. So he suggested three different types of mechanisms that are possible. So first, let us see the ionic mechanism. So let us take here the two reactants that has to be taken. Okay. So here we have the conjugated diene. Along with that, we have the dienophile. So now this moves here, this attacks here, and from here, see this attacks here. And of course, this I can show it directly instead of showing it in two steps. So this attacks the carbon over here. So since it is an ionic mechanism, so we are going to show this formation of bond because of the ionic nature. But actually, it's not ionic here, but still, since we are considering that under ionic mechanism, we are showing the structure in this way. And finally we are going to get the cyclohexene. It can also be shown with respect to free radical mechanism. Free radical mechanism. So again, I take the diene, conjugated diene, and the dienophile. So here, this can shift here, this can shift here again, and the double bond can shift here by free radical mechanism. That is by homolytic cleavage. Now you get this structure. Here there will be a free radical, and here there will be a free radical. Now, because of which a bond is formed here. So you get finally the cyclohexene, right? So this is with respect to the two mechanisms, that is ionic mechanism as well as the free radical mechanism. Now let us look into the most commonly followed mechanism, that is the concerted mechanism. So let me write it here itself. Concerted mechanism. Yes. So here, yes. So we have the conjugated diene. Along with that, we also have this, right? So now this attacks here, this comes and attacks here, and this shifts here, right? So let me also take the substituents here. So let me take R and R dash, right? So we have the compound, the final product, that is here double bond, and here R and R dash, right? So here also cis addition takes place in this particular case. And in case of cyclic dienes, two cis addition, that is exo as well as endo, are also possible. Next, talking about the Friedel-Crafts reaction. So here it involves the introduction of an alkyl or an acyl or an aryl group into the aromatic ring. So here mainly we need to take the Lewis acid. So you can take anhydrous aluminum chloride, the ferric chloride, or a protic acid as a catalyst. So the alkyl, acyl, or the aryl group is introduced into the ring. So let us write the general reactions. So let me take benzene. So we have methyl chloride in the presence of anhydrous aluminum chloride catalyst. So here the methylation takes place. The methyl group is introduced into the ring. So we have CH3 along with that HCl. So this is nothing but alkylation. The alkyl group is introduced into the ring, right? So alkylation. Along with that, acylation also can be done. So CH3, COCl in the presence of anhydrous aluminum chloride. So now the acylated product is obtained. So we have COCH3, right? Along with that, HCl is the byproduct. So this is acylation. So here we get the toluene. Here we are going to get the acetophenone. Now coming on to the mechanism. So let us look into the mechanism for alkylation. Yes. So first, let us take the alkyl halide, RCl. Now, in the presence of aluminum chloride, so what is going to happen? You're going to get AlCl4 minus and R plus. The carbocation is obtained. Now, we take the benzene and treat it with R plus. In the presence of R plus, what is going to happen? This will come and attack here. So, the plus charge, you can write it in this way. So R and H will attach to this carbon. Now, in the presence of aluminum chloride, the AlCl4 minus, the aluminum chloride, which has abstracted one chloride ion, so it has become AlCl4 minus now. Because we know that AlCl3 is a Lewis acid, so it abstracts a Cl minus and it has become AlCl4 minus. Now we are going to get here. So this will abstract the H, and now you're going to get here the R group that is attached to the ring along with that HCl and AlCl3, right? So this is how the alkylation takes place. Now talking about acylation. Acylation reaction. So similarly, you can also take here first the benzene. Before that, let us see CH3, COCl you're going to take in the presence of again aluminum chloride. So you're going to get the CH3CO plus along with that AlCl 4 minus, like how we have discussed in the previous case. So now it will be CH3 CO plus. So it is actually the carbocation, although we write it here. Let me write it clearly to make it more clear. So the plus charge is on the carbon actually. Okay. So now again this attacks this carbon. So what you're going to get, like how we have written for the previous one, the same thing here. COCH3, and here we have the H also. Now in the presence of AlCl4 minus, now this abstracts the H, because of which you're going to get here COCH3, along with that AlCl3 and HCl, right? So suppose you use N-propyl chloride, then what you're going to get as the product. So we have seen about the general mechanism of alkylation and arylation. So now let us see, suppose we take CH3, CH2, CH2Cl, that is N-propyl chloride, in the presence of again AlCl3. You're going to get CH3, CH2, CH2 plus the carbocation, along with that AlCl4 minus. So this is a primary carbocation. Now it can rearrange in such a way that a more stable carbocation, that is the secondary carbocation, can, can form from this primary carbocation. So how it takes place? So let us see CH3. Now this H can be written in this way. Here CH2 plus. Now this can shift here. So because of which you get CH3, CH, here plus charge, CH3. This is nothing but the secondary carbocation, right? So now this secondary carbocation will go and attack the benzene ring. Okay, so CH3, it is not going to attack, but the double bond in the benzene ring will attack this car, which is bearing the positive charge, right? So we're going to get your H, your CH, CH3, CH3. So again plus. Now this in the presence of AlCl4 minus, this abstract this hydrogen. So because of which you're going to get the CH, CH3 and CH3. Okay. So here you're going to get the major product, that is isopropyl benzene, because of the rearrangement that is taking place, and because the secondary carbocation is more stable when compared to that of the primary carbocation. So based on this, the benzene, the electrons, the pi electrons that are present in the benzene, it attacks from the ortho position the carbon. So what happens is the attack takes place to the carbon bearing the positive charge, that is mainly the secondary carbocation, because of which you get the isopropyl benzene as the major product. So suppose you're using low temperature, then the N-propyl benzene is predominant, and the proportion of isopropyl benzene, it increases when the temperature is increased. So this is also one more thing you need to remember clear, right? Next, coming on to the Wittig reaction. So it is a general method for the synthesis of alkenes, and it involves the reaction of an aldehyde or a ketone with a phosphonium halide. Okay, that is alkylidine triphenyl phosphorane. So the general reagent that we take is PH3P double bond CHR, which is also called as the Wittig reagent or the halide. And here the carbonyl oxygen is replaced by an alkylidine group. So again here the selective carbon-carbon double bond formation takes place because of this reaction. So let us take the general reaction. So PH3P, that is triphenyl phosphorane, alkylidine triphenyl phosphorane is taken. So double bond CH2. Along with that, you're going to take the aldehyde or the ketone. So let us take PH2 C double bond O. You're going to take the ketone here. So you're going to get PH2C double bond CH2, because finally we're going to get the alkenes, right? General method of preparation of alkenes. So we are going to get the alkenes, and along with that, the PPH3 double bond O that we get as the byproduct. Okay, so let us look into one more example. So PH3P CHR dash. So we take one more substituent. So here, if I take R2 C double bond O, so you're going to get R2 C here double bond and whatever is present here, that is CHR dash. Along with that, PPH3 double bond O. So coming on to the mechanism of this reaction, so let us take PH3P double bond, let us take Cr2. So this can also be written as PH3P, here plus charge, single bond, Cr2, here minus charge. So now I'll take the carbonyl compound. So C double bond O, here R dash, R double dash. Now this minus charge can attack this carbonyl carbon. Now this shifts here. So this can also be written as PH3P, here Cr2. Here I have now the bond that is formed between the carbon, two carbons. So here R dash, R double dash. So here O minus. Now this O minus, so here there is a plus charge. Now O minus, it can attack here. So because of which you're going to get this cyclic structure. So P here, there are two R groups that are attached here. Now the carbon here R dash, R double dash. Now here we have oxygen and the bond here. So this can shift here because ultimately we want the double bond over here. Now this shifts here because we get PH3 P double bond O, right? So we get the two products. So PH3 P double bond O. Along with that we have C, R and R double bond C, R dash, R double dash. That is the alkene as the product. So suppose you take PH, P plus here Cr2, the minus charge. So suppose you treat it with R2. Okay, let me take the dash, R dash twice, C double bond C, C double bonds O. That is nothing but ketene, right? So if it is treated with ketene, you get R2, that is double the R dash 2, carbon, double bond C. Now this will break and it will form the double bond with this group, Cr2 group. So you get double bond Cr2. Now, we can also treat it with R dash N double bond C double bond O, that is isocyanate. Isocyanate. So you get again R dash N double bond C. Now this will be removed and it will form the bond with this PH3P. So sorry, this should be PH3P. Okay, so now the Cr2 will come and form a double bond here. So here you're going to get Cr2. So we have seen clearly in the mechanism how it goes about, right? So next R dash N double bond O, that is a nitroso compound. Nitroso compound. So again, it is very simple to predict the product. So this bond breaks here. This is going to join with the PH3P part of the molecule. So you get R dash N double bond Cr2. So again, if you're going to treat it with R2, let us take R dash twice C double bond NR, that is imine. You're going to get R2, that is R dash twice C double bond Cr2. Okay, so these are the applications of this Wittig reaction. Next, coming on to Robinson annulation, that is cyclization reaction. So here, it converts the cyclic ketone into a fused cyclic ketone, which contains an additional 6-membered ring with a double bond. And this particular reaction, it involves a Michael addition, which is followed by an intramolecular aldol condensation reaction, and it is again useful for the synthesis of fused ring systems. And this is particularly useful in the synthesis of steroids and terpenes. So let us look into the reaction. Know that we take a cyclic ketone. So I start with cyclohexanone. In the presence of base, so what is going to happen? This O will become O minus and the double bond will shift inside. So I'm going to get here O minus and here this becomes a double bond. Now when it is treated with here the other reagent, okay, because it is a Michael addition that is happening in this particular reaction. So Here we have the Michael addition. So because of Michael addition, you're going to get here the benzene ring. There is a double bond O that will be formed from this. Now this bond, if this carbon will attack the ring, because of which you get here, and the ketone group is present here because of the attack of the carbon to the ring. Right. So now the internal aldol condensation will take place. Okay. So now what is going to happen? Here there is this is nothing but the CH3. So in the presence of a base, it can form CH2 minus, right? So let us see how it takes place. So here there is a carbonyl group. So here double bond O. Here it becomes CH2 minus in the presence of a base. Now this shifts here, this shifts here. Now you get here. Now this becomes the carbon joins this particular ring. And here there is a double bond. And here the ring. So now this becomes OH. Now what happens is, again, in the presence of, if it is heated, the water molecule can be removed off. So what you're going to get, here there is hydrogen, right? There will be hydrogens that are present. So this can shift here. OH can be removed off. So here the fused ring system is obtained. Here there is a double bond that is present. And here there will be there is double bond O, and in conjugation with that of the double bond O, you have a carbon to carbon double bond. Right. So this is how the Robinson annulation takes place. Next, coming on to the Ene reaction. So Ene reaction, it involves the addition of an olefin having an allylic hydrogen, okay, and the enophile, with the enophile, that is to the compound having a double bond. So it can be C double bond C, C double bond O, or N double bond N, multiple bonds. So this reaction between the olefin as well as the enophile is called as the Ene reaction. And here a new sigma bond is taking place at the terminal carbon of the allyl group. Now, it is followed by 1,5 hydrogen migration and shift of the double bond, and this overall reaction is reversible. Along with this, we should also remember that intramolecular Ene reactions are also possible. So let us look into the general reaction. So here we have double bond, there is H, double bond here, that is here C double bond C that we have used, that is nothing but the enophile. So we take the olefin, that is allylic hydrogen should be present, and then we take the enophile. Now, because of the Ene reaction, we are going to get here this particular product. So let us look into the mechanism of this reaction. So we take the olefin, which has the allylic hydrogen. Along with that, we take the enophile, right? So you're going to get the transition state in this way, right? Then, which leads to the formation of the products. So here you get a double bond here and the hydrogen. Now this reaction is also reversible, as I already told. So you can get back the reactant. Suppose you take the product, heat it at 400 degrees Celsius, you can get back the product. Along with that, the enophile that you have taken back, you can get it back. Now, intramolecular Ene reactions are also possible. Suppose we have the substrate in this form. So here there is an allylic hydrogen that is present, and also there is an enophile that is present within the same molecule. So you heat it 475 degrees Celsius. So you're going to get the transition state here. So the hydrogen that is there, your double bond, your a double bond. So this hydrogen can shift here, and this can shift here. So because of which you get the product here, the cyclic structure, here CH3, along with that, the hydrogens, right? So next, coming on to benzoyl condensation. It is a self-condensation reaction of the aromatic aldehydes which do not have the alpha hydrogen. So cyanide ions should be present in this reaction, which acts as a catalyst. and we get the product that is alpha hydroxy ketone, which is nothing but benzoin as the product. So this is also an important carbon-carbon bond forming reaction. So let us talk about this, the general reaction of this benzoin condensation. So C6H5CHO in the presence of cyanoions, that is cyanide ion, and heat, we have, again, we need to take the solvent. Let us take ethanol and water. So we get the benzoin, C6H5, C double bond O, COH, here also there is one H, and C6H5, which is nothing but the alpha hydroxy ketone. So here we have the ketone group. In the alpha position, there is a hydroxy group, which is nothing but the benzoin. So let us look into the mechanism of this reaction. So let us take PH, CH, double bond O, which is the benzaldehyde. Now in the presence of cyanide ion, so here we know that Cn minus can attack the carbon in carbon and the shifts here. Again, we need to take the aldehydes without the alpha hydrogen atom. So obviously the attack occurs at the carbon in carbon. So now we have PH. Here there is H, right? So here there is O minus and here there is a Cn which is attached. Now this H, so here there is O minus, right? So it can abstract this H. So what is going to happen? So pH, now if it abstracts the hydrogen, this bond shifts here. So you get C minus here, there is Cn, and here there is OH, right? Now there is one more benzaldehyde which we need to consider. Now this minus can attack the carbon and again it can shift here. So I can write it as here pH, here carbon, there is OH, right? That is attached to the carbon here. There is Cn which is attached. Along with that, the carbon also has attacked this carbon, the carbon in carbon. So C, here O minus. Now H is also present here. And along with that, there is pH. Now, here, what happens is this can shift here because the negative charge, the O minus can abstract the hydrogen. So I can shift this bond here. So because of which I can write it as pH here. Now this has shifted here. So I get double bond O, right? Now here, since this bond has shifted here, the cyano group can be easily removed. So Cn minus is removed off. Now what is remaining here? This O minus has abstracted the hydrogen. So here I get OH. Here there is H and here there is pH, which is nothing but the required product, that is benzoin. That is alpha hydroxy ketone. Yes. Coming on to the next one, that is Clemmensen reduction. So it is a reduction reaction in which the aldehydes and the ketones, that is the carbonyl group of the aldehyde and ketone, directly converts into the methylene group. That is reduction of the C double bond O to CH2 group takes place in the presence of concentrated HCl and zinc amalgam. So here it converts the carbonyl compounds into the alkanes during this reduction process. Coming on to the mechanism of this reaction. So let us take the carbonyl compound in the presence of zinc and HCl. So Cl minus from the HCl. So what is going to happen now? So you get RCO minus. Now the ZnCl will come and attack here. And here there will be R and R dash. Let me take one more as R dash. So in the presence of H plus, now what is going to happen? You have R, C, here OH. Let me take one more as R dash. Now ZnCl. Now in the presence of H plus, this lone pair of electron can attack here and the H2O can be removed off. So because of which the carbon will get the positive charge. So R dash, here ZnCl. Now in the presence of zinc, you are going to get here R, C R dash. Now this becomes minus charge, ZnCl. Now again, because H plus, that is the acidic condition that is used. So because of that, you get RCH R dash, here ZnCl. And finally, on hydrolysis, you're going to get RCH2 R dash. Okay, so this is the hydrocarbon that we get from the carbonyl compound, which was taken as the starting material. So next, coming on to Wolff-Kishner reduction. This involves the reduction of aldehydes and ketones to the alkanes like that of Clemmensen reduction. But here, this reaction is carried out in the presence of a strong base like NaOH or sodium ethoxide, whereas Clemmensen reduction is carried out in the acidic conditions. Here, hydrozones, semicarbozones or azynes are involved as intermediates, and the C double bond O group is completely reduced to the CH2 group in this reduction process. So let us write the general reaction. So C double bond O, that is the carbonyl compound. Let us take NH2, NH2. Now, here we know that the H2O removal of water molecule can take place. So because of which you get C double bond N. Here again NH2. Now in the presence of a base like sodium ethoxide, C2H5ONA, or sodium hydroxide, and on heating, you're going to get the C double bond O is converted into CH2 group. Along with that, the nitrogen gas is evolved. So let us take the specific example. So CH3, CH2 5 times, C double bond O, CH3. When we are going to take the ketone, now NH2, NH2, heat, and then the second step, treating it with the base. So here, this C double bond O is converted into CH2 group. So we have CH2 6 times CH3, right? So let us look into the mechanism of this reaction. So C double bond O, let us take R and R. Then we are going to take this NH2, NH2. So first, what happens is, we know that the hydrogen H2 as well as oxygen, these both are removed out as water molecule. So removal of water molecule. So you're going to get here R and R. So this will be C double bond N, NH2, right? Now in the presence of a base, let us say sodium hydroxide. So this one of the hydrogen will be abstracted by the base so as to get here. Let me show it clearly in this step itself. So if I take here H and H, so one of the hydrogen is abstracted by the base and this becomes N minus. So I can write it as R, C, R, here double bond N, here N minus, right? And there is one H also that is there along with the nitrogen. So now this can also, see, this charge can shift here and the bond can shift to the carbon so that the carbon gets the negative charge. So I can write it as here, this as minus charge, here N double bond NH, right? So now this on treating with R dash OH. So what is going to happen? So here R, R, then here you're going to get this H, along with that here N double bond NH, right? So because here there is the minus charge that is there, so it abstracts one of the hydrogen, right? So now again on treating with OH minus, so what is going to happen? See, this hydrogen will be abstracted by the base. So R and R, so H here, so N double bond N. So here there will be a minus charge because the hydrogen is abstracted by this. So this bond shifts to the nitrogen. So that's why you get the negative charge here on nitrogen. Now this can shift here, and here this bond can shift back to the carbon so that you get R, R, here H and minus charge. So this again on treating with R dash OH. So you get R, here H and H, right? Or CH2. So it is very clear that the C double bond O group is reduced to CH2 group in this Wolff-Kishner reduction reaction. Next, coming on to Mirvin-Pondorf-Verley reduction. So it involves the reduction of aldehydes and ketones to the corresponding alcohols. So mainly we use the aluminum isopropoxide in the presence of isopropyl alcohol. And it is a mild and selective reduction method and opposite to that of the opionure oxidation, about which we will be discussing a bit later. So let us look into the general reaction. So RCO, R dash in the presence of isopropanol. So we are going to write it as CH3, CHOH, here CH3. And of course, we are going to take the aluminium isopropoxide. So ANOCH Me twice, 3 times, right? So we have R. So this aldehyde or the ketone. So in this case, we have taken the ketone. So carbonyl compounds are reduced to the alcohols. So here in the general reaction, since I have taken the ketone, so I have to write it as CHOH R dash. Along with that, we get the acetone. Okay, so this is with respect to the MPV reduction. Let us look into the mechanism. So we have R and R. So C double bond O, let me write it so that the writing structure will be easier for me. So along with the aluminium isopropoxide, so aluminium, so we have OCH Me twice, so here twice. So let me write one of these groups separately. So OCH Me twice, so that I can show the mechanism, how it is taking place. So now this along with the electron pair comes and attacks this carbonyl carbon. Now this double bond, so the electrons from the double bond will attack the aluminium. So now this bond shifts here, right? So because of which you're going to get R, here R dash. So let me take R dash here. So now this double bond is broken to a single bond. So let me write here single bond. But I'm just showing the dotted lines because one of the bond is breaking, right? Now a bond is formed from this oxygen to aluminium. And of course, the aluminium is bound to this OCH Me twice, 2 times, this group, right? And this bond is going to break. So let me show a dotted line again. So oxygen. Now here a double bond is going to be formed, but one bond is already there. One double bond is going to be formed. So here we have methyl groups, 2 methyl groups. Now here this bond is going to break. So let me show a dotted line, right, with the hydrogen. Now here this hydrogen is going to attach with the carbon. So let me show a dotted line. So this is just what happens, how the bonds are broken and how the new bonds are formed. So wherever the bonds are broken and new bonds are formed, those bonds I have represented with dotted lines. So this can also be represented like this. So R, C, R dash, right? So here now it becomes, so here this becomes a bond is formed here. So O, A, N, O, C, H, M, E twice, 2 times. Now here the H, now this bond has broken, so it becomes C double bond O, and this bond also has broken. So you're going to get the acetone, right? Me, C double bond O, Ne, right? So now let us look into what happens next. So we have R, R dash. So we have H, and here OAN, OCH, Me twice. So this on hydrolysis, you're going to get the alcohol, right? So here OH and H. Along with that, you're going to get back the aluminium isopropoxide. So next, coming on to the Birch reduction method. So this involves the reduction of the aromatic rings using alkali metals such as lithium, sodium, or potassium in liquid ammonia. So mainly it gives unconjugated dihydroderivatives. So unconjugated 1,4 cyclohexadiene derivatives. And the addition mainly takes place at 1 and 4 positions. So let us look at the examples. So if I take benzene in the presence of lithium and liquid ammonia, and if I use ethanol, so here at the 1,4 positions, the addition takes place. So you're going to get here, let me start numbering 1, 2, 3, 4. So 1, 4 cyclohexadiene, right? So this is a cyclohexane ring. There are 2 double bonds, so diene, and the 2 double bonds are in the 1 and the 4th position, right? So that's why 1,4 cyclohexadiene. So let us take one more example. So we are mainly looking at the aromatic rings. So it can be fused rings also if you are taking like naphthalene. So Again, lithium in the presence of liquid ammonia and ethanol. So here, one of the rings, the aromaticity is intact, whereas here the addition takes place. So you get a compound in this way, right? So suppose you take benzoic acid, COOH, again sodium, liquid ammonia, and you take ethanol. So here you're going to get, again, 1,4 addition takes place. The COOH group will remain as such. So let us look at the mechanism of this reaction. So let us take benzene ring. So here the double bonds, right? Now there is lithium. Now lithium has one electron in the outermost shell, right? So now what happens is that here using this one electron, it attacks the benzene ring. So this bond shifts here. And because of which, now what happens is, here I can write it as, here the bond is used for shifting. So this becomes negatively charged. Here it has become the charge. Now here there is H. Now lithium has used only one electron. So one electron, I'm going to write it here. These bonds remain as such. Now this can also be written as here. So it can be written as C. If this is shifted here and this bond moves here, I get here the double bonds. Here there is minus charge. And here the hydrogen with one electron remains intact. I can also write it as, if this bond shifts here and this bond shifts here, so this becomes minus charge, the negative charge. Here there is hydrogen and this electron. And of course, these two bonds are in this positions. Now, in the presence of ROH, that is, if you are taking ethanol, so now I can write this as, so here, let us take this particular structure. So in the presence of alcohol, now I have the two hydrogens that are present here. Now here, the two bonds, the hydrogen as well as the single electron that is present. Now again, lithium is present because it is a reagent that is used here. So now it also has one electron in the outermost shell. So again, this can pair up with the one electron that is present. So because of which you can get a negative charge here on this particular carbon, and the other atoms and the arrangements remain the same. Now, again, in the presence of ROH, that is the alcohol or ethanol, what you're going to take. Now, this minus charge will be converted into, so here the hydrogen is going to attach because here ROH, so this H can attack there. So because of which you're going to get here the two hydrogens and here the two bonds that are there. So because of which you're going to get the 1,4, the dihydroderivative. Next, coming on to Cannizzaro reaction. So this reaction is mainly shown by the aldehydes which do not have the alpha hydrogen. They undergo self-oxidation and self-reduction in the presence of concentrated aqueous alkali, right? So here mainly you're going to get the alcohol and the salt of the corresponding carboxylic acid. So one molecule is oxidized to the salt of the corresponding carboxylic acid, whereas the another molecule is reduced to the corresponding alcohol. So let us look into the examples. So if I take formaldehyde, because here the main criteria is the alpha hydrogen should be absent. So let us take two molecules. So if I'm talking about the entire reaction as such, so let me take 2 moles of HCHO, formaldehyde, in the presence of NaOH, because we are going to use the concentrated aqueous alkali. So you're going to heat it. So there will be reduction as well as there will be oxidation. So because of which you're going to get an alcohol. Along with that, you're going to get the sodium salt of the carboxylic acid. So here I've used sodium hydroxide. So sodium salt of the carboxylic acid. So formic acid you're going to get. And the one more product is methanol. So if I take now benzaldehyde, so C6H5CHO, here also there are no alpha hydrogens that are present. So NaOH on heating. Now there is a reduced product as well as the oxidized product. So you're going to get C6H5, CH2OH. Along with that, you're going to get C6H5COO. right? Now, there are a few aldehydes which have alpha hydrogen, but still they can show Cannizzaro reaction. Just write a reaction here itself. So, dimethyl acetaldehyde. So, CHO. So, there is an alpha hydrogen that is present here. It is very clear. Now, even though this particular aldehyde has an alpha hydrogen in the presence of alkali and on heating, you're going to get the two products based on the Cannizzaro reaction. So, you're going to get CH3 twice CH2OH, that is the alcohol. Along with that, you're also going to get the sodium salt of the carboxylic acid, that is CH3 twice CHCOON. Okay, so there are a few exceptions. So as I've already told, one of the examples is where this dimethyl acetaldehyde, although it has an alpha hydrogen, it shows Cannizzaro reaction. Now, moving on to the mechanism of the Cannizzaro reaction. So, let us take the aldehyde, right? So, this in the presence of the alkali. So, it can be sodium hydroxide or potassium hydroxide. So, now this OH attacks here and the bond shifts here. So, because of which you're going to get R, C, here O minus, here the OH as well as H, right? So, now this again, so RCO minus H and OH. So take one more molecule of the aldehyde. So now what is going to happen? Here, first this comes back, right? And here, along with the electrons, this attacks the carbonyl carbon, and here the bond shifts here. So because of which, just look at this particular structure now. Now R, this becomes double bond O, right? RCO, and there is OH. The H has been removed off. So you already got the carboxylic acid, but we need the sodium salt of carboxylic acid if you have used the sodium hydroxide as the alkali. Now let us keep it as such. What is the other species that we get? So here R, C, this becomes O minus, and here there is H. Now this H also has attacked here, right? Now, here we have got the alkoxide ion, and we've got the carboxylic acid. But the products of the Cannizzaro reactions are, that is the carboxylic sodium salt of the carboxylic acid and the alcohol. So now there will be proton exchange. So here the hydrogen will be abstracted and this bond shifts here. So because of which you get RCOO minus. So this minus charge, of course, if it is sodium hydroxide that is used, so you get the sodium salt of carboxylic acid. Along with that, you get RCH2OH. So this is the mechanism of the Cannizzaro reaction. So now, suppose if the alcohol is used as a reaction medium, or in other words, if an alkoxide is used in the Cannizzaro reaction, then we get an ester as the product. So let us write the reaction. So C6H5 CHO benzaldehyde in the presence of C6H5 CH2ONA. So where you're going to use the alkoxide ion. So in the presence of the corresponding alcohol, C6H5, CH2OH, you're going to get the ester, that is C6H5, COO, CH2, C6H5. Now, when two different non-enolizable aldehydes are present, then they also undergo crossed Cannizzaro reaction. So, if both the aldehydes, they do not have the alpha hydrogen atoms, then they can undergo cross Cannizzaro reaction. So, let us consider. So, C6H5, CHO, HCHO in the presence of sodium hydroxide and heat. So, you're going to get C6H5, CH2OH, that is alcohol. Along with that, you're going to get the sodium formate that is obtained as the product. So suppose you have dialdehydes, then they can undergo intramolecular Cannizzaro reaction. So let us take the example of glyoxal. So here one aldehyde group and another aldehyde group. So H and double bond O in the presence of NaOH. Now, one of the aldehyde groups is reduced to alcohol. The other aldehyde group is oxidized to the carboxylate ion. So, here CH2, here OH. Now, the other aldehyde group is oxidized. So, O and here double bond O. Next, coming on to opional oxidation. So, oxidation of a secondary alcohol to give the ketone by the interchange of the alkyl groups of acetone as well as the secondary alcohol in the presence of, again, we are going to take aluminium isopropoxide or aluminium tertiary butoxide in the presence of acetone. It is called as opional oxidation. So, here it involves the hydride transfer between the alcohol and the acetone so that the alcohols will be oxidized to ketones. So especially we are going to take secondary alcohols here. So they undergo oxidation to give the ketones. So let us take the secondary alcohol here. So R2CHOH, that is secondary alcohol, in the presence of ketone, that is CH3 twice, C. In the presence of aluminium isopropoxide, we are going to get the ketone because the secondary alcohol will be oxidized to ketone. And then here the acetone will be reduced to the alcohol. So OHCH3, right? So similarly, I can also take R2CHOH, secondary alcohol, in the presence of cyclic ketone. So again, aluminium isopropoxide. So here we are going to get the ketone and the cyclic ketone will be reduced to the secondary alcohol. Again, the cyclic secondary alcohol, that is, this is nothing but cyclohexanol. So this is cyclohexanol, right? Yes. Next, coming on to the Mannich reaction, it involves the condensation of a compound containing at least one active hydrogen atom, formaldehyde, and ammonia or a primary or secondary amide, and usually as its salt, that is ammonium chloride. So the compound formed in this reaction is called as the Mannich base. So it is nothing but a beta amino carbonyl compound that is formed. And here, this reaction is mainly catalyzed by either an acid or a base. So tertiary amines, they do not undergo the Mannich reaction. So we are mainly concentrating on ammonia or a primary or a secondary amine. Right. So let us write the general reaction. So R, C double bond O, CH3. So along with that, we are going to take the formaldehyde. So H, CHO. And we can take the ammonia or the primary or the secondary amine in the form of its salt. So let us take NH4Cl. So here acid or base catalyzed. So H plus or OH minus. So here you're going to get R, C double bond O, CH2. Here CH2 dot NH2 HCl, which is nothing but the Mannich base. Okay, Mannich base. So I can take one more specific example. So C6H5, CO, CH3. Next, you're going to take formaldehyde. Along with that, the salt of the, so you can take the amines in the form of their salts. So CH3 twice, NH2 plus Cl minus. Now here you're going to get again in the presence of acid or a base. So C6H5, C double bond O, here CH2, CH2, here NHCH3 twice Cl minus. So here nitrogen will have the positive charge. Along with that, water is removed off. So again, you're going to get the Mannich base. So when I'm talking about the aryl amines, they do not give this reaction. The aryl amines cannot be used for this purpose. Now the amines that can be used may be primary or secondary, but most conveniently we take the secondary amines since they possess only one replaceable hydrogen atom so that the reaction proceeds smoothly. The product with the primary amine is secondary amine Mannich base, which further reacts to give the tertiary amine. Okay. So now let us look into the mechanism to understand it in a better way. So first let us look into the acid catalyzed mechanism. So let us take a ketone. So here this is in the keto form. This can also exist in the enol form, right? So one of the hydrogen can shift here. So I can write it in the enol form. So let me write it directly. So OH double bond CH2. So how the keto-enol tautomerization takes place. So this I've explained already in this video itself with by taking one of the examples in the previous reaction. So you can go through that. So now I've got the enol form. So let us take the formaldehyde, that is C double bond O, H and H. This in the presence of, let us say, the secondary amines. So as I already told, the secondary amines are the best to be used for this reaction because they contain only one replaceable hydrogen. So when I take this, now what I'm going to get here, so here what happens is there is a lone pair of electrons that is present here. So it can attack this carbon in carbon and this bond can shift here. So now this can become OH, right? Now here there is H and H that is present. Here there is nitrogen that is attached to it and R and R. There was a plus charge, but now this H can go and attach with this O minus. So because of which I can neutralize it. Right, I'm not going to show two steps. So directly I've written N with two R groups attached. And here instead of writing O minus, I've written it directly as OH. I hope it is clear. So now this in the presence of H plus, because now I'm talking about acid catalyzed reaction, acid catalyzed, this particular reaction catalyzed by the acid. So H plus. Now what is going to happen here? There is a lone pair of electrons. So this can abstract the H plus and you get here H and H. So here OH2 plus N and R. So this can be removed off, right? So because of which you get CH2. Here there will be the plus charge that is present along with that En and R, right? So now what happens is, so now there is the removal of water molecule. So let me write here H2O is removed off. So now here this lone pair of electron can shift here. So because of which I can also write it as H and H. Here double bond N, R and R. So here there will be a plus charge now. Okay. So now let us take this enol form of the ketone. So CH2 double bond COH, here R dash, right? So what I'm going to get is, so R dash C, here there is OH. So now what is going to happen? So now we know that here there was a plus charge, right? So this double bond can attack the carbon. This bond can shift to neutralize the nitrogen, the charge that is present on nitrogen. So here we get COH, right? Now this, the double bond has, the electrons from this double bond has gone to attack the carbon. So because of which this gets a positive charge. Now there is CH2, right? There's also one more CH2. So CH2, which is further attached to Nr2, right? Now here there is a plus charge. It can be neutralized by this loss of H plus. So because of which I'm going to get R dash C double bond O CH2 CH2 Nr2, right? Which is nothing but the mannich base. So suppose we are talking about the base catalyzed reaction. So let me write it here itself. The base catalyzed reaction, right? So we are going to take again let us take the ketone again, RCOCH3. Now we know that in the presence of the base, so let me take ETO minus. So one of the hydrogen will be abstracted. So you can get RCOCH2 minus because there is alpha hydrogen which can be easily abstracted off. So along with that, you're also going to get ETOH, ethanol, right? So now I have to take formaldehyde also. So C double bond O, H and H. Now this in the presence of the secondary amine, so R and R along with that H. So this lone pair, it can attack the carbon in carbon and the bond can shift here. So you're going to get here carbon, H and H. This becomes OH. So along with that, you get N, that is with R and R. Right. So now we have this particular and carbanion that is present, right? So it can attack this particular compound that is formed. So here CH2 minus C double bond O R. So this can attack this carbon, right? And this OH can be removed off because OH is a leaving group. So because of that, this carbon is attacked. So now you get NR2. Now to this NR2, what is attached? CH2 is attached. Now to this CH2, there is one more CH2 that is attached. Along with that, C double bond to R, right? So most favorable mechanism is the acid catalyzed, but even in the presence of base, this particular reaction can take place. Next, coming on to the Michael addition reaction. So the addition of the compounds containing active methylene group or relatively the acidic hydrogen if they are present in the compound in the presence of a base catalyst to an activated olefinic bond of the type C double bond C, here X, where X is an electron withdrawing group, is called as Michael addition reaction. So let us look into an example. So C6H5 CH double bond CH, COO, C2H5. Along with that, if I'm taking malonic ester, so CH2, COO, C2H5, again COO, C2H5. So C2H5 ONA, oxide ion. So you're going to get C6H5, CH, here CH2, COO, C2H5. Now here it will be CH, COO, C2H5, COO, C2H5. Okay, so this is nothing but the Michael addition reaction. Now let us look into the mechanism of this reaction. So these are the examples of the activated alkenes, right? And the examples of the Michael donors can be malonic ester, cyanoacetic ester, or acetoacetic ester. The base catalysts that can be used are sodium methoxide, or you can also use secondary amides. So you can also use especially the piperidine as the common base catalyst. Right. So let us look into the mechanism. So let us take malonic ester. So CH2, COO, C2H5. Here also COO, C2H5. In the presence of base, okay. So what you're going to get? So in the presence of the base, this one of the H will be abstracted by the base. So you're going to get here CH minus, COO, C2H5, COO, C2H5. Now, what is going to happen? So here you're going to get the carbanion. Now, let us take R2, here C double bond. So here double bond R. So here one more R. So you can take any of these, right? So as I already told, you can take the alkene compounds, that is the acceptor. So you can take any of these. You can take RCH double bond CH, CHO, this kind of compounds. You can take RCH double bond CH, COR dash. You can also take RC double bond CH, COOR dash. Okay, CH. So you can also take RCH double bond CH, CN, where cyano group or ester group, ketone, aldehyde, you can take any of these substituents. Because of that, you can take any of these substrates for this particular reaction. So let us take, now in this reaction, I'm showing the mechanism for this particular type of compounds. Okay, so let me erase this. This was just for you to be familiar with what are the substrates that can be taken along with whatever I'm showing it in this mechanism. So here, this carbanion, it attacks. So COO, C2H5. Here, COO, C2H5. Here, there is a minus charge. Now, this can attack this carbon. Now, this can shift here. This can shift here, right? So, because of which, this is a rate determining step. One more thing you need to remember. Now, so R1, R2. Now here the carbon. So this becomes a single bond now. So carbon. And here there is the CH group that is attached along with the COO, C2H5 and COO, C2H5. Right? Now there is carbon that is attached, and to this carbon there is R that is attached. Now this became a double bond. Here carbon, again there is an R, and here this becomes a minus charge, right? So now this in the presence of the base, so base has already abstracted the proton. So in the presence of this, so now what is going to happen? This O minus will get converted into the OH. So you get R2, here R1. So CH, I can write it as COO, C2H5 twice. So now here CR, double bond CR, here you have OH, right? So this also can exist in tautomerism with the keto form. So I can write it as R2, here R1. So again CH, here it's the same, COO, C2H5 twice. Now here there will be, yeah. So now if I'm talking about the keto form, see this is now this can shift here and here it can shift so that the H can be attached here. So I can get here CHR, single bond, here again CR, now double bond O. Okay, I hope it is clear how the tautomerism can occur and how the keto enol. So this is in the enol form and this is in the keto form. Okay, so this is how we are going to get the products based on the Michael addition. So we're going to look into the substrates. So you need to remember one simple criteria that is required here. The double bond should be in conjugation with the functional group, that is C double bond O or C triple bond N, whatever you're going to take. So substrate should have this conjugation, and along with that you're going to take the base. So you can take any of the bases. So piperidine is the best one that can be used. Along with that, you're going to take a compound with active methylene group. Right. Now, if the compounds contain two double bonds which are conjugated with a carbonyl group, they react with the active methylene compounds to give 1,6 addition compounds. Okay. So we can take an example for this. So here CH2, CH double bond, CH. Here if I'm taking a carbonyl group, that is carbonyl group is present here, but it's not exactly an aldehyde or a ketone. We are taking an ester, but there is C double bond O group. Now you can see there is here this double bond, there is one more double bond, and these two double bonds are in conjugation with the C double bond O group. So in such cases, you're going to get the 1,6 addition products. So if you're going to treat it with CH2, COO, CH3 twice. So in the presence of a base, so let us take ethoxide ion, that is sodium ethoxide. So you're going to get CH3O twice CH, CH2, CH2, CH double bond CH, COO, CH3. So 1,6 addition products are obtained when methyl vinyl acrylate reacts with dimethyl malonate, and you're going to get this particular product, right? So I hope this particular video is useful. So I've explained all the name reactions in detail with the mechanism for each of the reaction. So thank you so much for watching the video. Subscribe my channel for more such informative chemistry related videos. Thank you.